Hello and welcome. Today I'm going to do a quick walkthrough of the Road to Las Vegas 2024 Battle 6, which happened earlier today. It's called The Simple Case by Michael Jarman, and this is Michael being a very funny man because Michael set one esports case before, which was Dicey Battle, which is a good candidate for the hardest uh, case ever set in an esports tournament, and so he said, "Oh no, I'm going to set a simple case this time around," and then set another brutally hard case. Um, so it is simple in the sense that it is easy to explain. You just have to do some basic math. Um, so we'll come back to the bonuses later, but so first we're just interested in summing the digits in a long number, and then we're interested in summing the digits of a number that we get if we add two numbers together, if we add two numbers together again, if we subtract one number from another number, if we multiply two numbers together, or multiply three numbers together, and so on. The challenge is, the reason that this is not trivial, is that Excel, I don't know why those are still there, is that Excel doesn't like to add numbers this big. So if we just add those two together, I don't know why it's gone black, but you can see it only keeps, I think the number is 15 digits of precision, and everything else is zeroed out. It's not that the product of these two numbers actually ends in whatever it is, 30 odd zeros. Uh, and so you have to find a way to navigate the limits of Excel. So that's what I'm going to do. I'm going to show you three things today. First, I'm going to show you the unintended solution, because it turns out this is frustratingly simple to do in Python if you know Python. So I'll show you that very briefly. Then I'm going to show you my take on the intended solution, which is a sort of Lambda heavy approach. Not what I came up with at the time, but the sort of refined, more elegant version of that. So first I'll show you kind of how it works, and then I'll show you how the lambdas were built. And then lastly, Michael mentioned that there was a last level to this. So this goes as far as multiplication and then exponentiation of very, very large numbers. But there was another level of this that he planned, but then did not end up including, which was to add division into the mix. So I'm also going to have a go. Well, I've already had a go. I'm going to show you how I had a go at the level 8 that never was. But let's dive on in. I've left a kind of pre-run version of each one of these in Python just in case I stuff it up, but because my Python is pretty rusty. But the idea is we just say Python, grab that cell. The cell automatically starts off as a string, and so a string in Python is an iterable, which means that you can iterate over the characters in the string. So then we can map a function to each character in the string, just like this. Map the int function, and the int function is going to take the integer value, but if you give it a text number, it'll just give you a number, and then we just need to sum up that map. So you're just saying apply the function that turns a string into an integer to every character in the string, and then sum them up. And that'll spin for a second, and then Control-Alt-Shift-M turns it back into a regular cell, and that clears that level. Then for the next level, you have to add up but no carrying. So you can just kind of do the digit sum to each one of these separately because nothing carries, but you can also just add them in Python. So again, py. So if I want to add this to that, remember they come in as strings. So first I need to wrap this in int to get the integer from that, and then I need to add to that the integer part of this, and then I basically need to do the same thing as I did in level 1, but first I have to wrap it in string to convert it back into a string before I can iterate over it. You can't iterate over an integer. Then we'll do sum of map of int to that, close, and copy down, and hopefully that'll work. And oops, sorry, Control-Alt-Shift-M to turn it into regular Excel cells. All right, so level 2, same thing, and we don't need to change anything because the difference between level 2 and level 3 was whether you had to carry or not, but we already had a solution that worked without for both. Then level 4, we have to subtract, and this is where the Python option really starts to build momentum because Python doesn't have the precision limits that Excel has, so we just change the operation, done. Okay, next level, multiplication. Let's come in here, change this to a multiplication sign, copy down, spins for a second. That's all done. If you had a go at this case, you will understand when I say that even just looking at myself doing this now, especially when I did it first earlier and realized it was this easy in Python, obviously I didn't realize until after the fact, was horrifying because this was a bloody hard case. And then finally, for the last level, we just need to do exponentiation. So we'll just get rid of the third because there are only 2 inputs. And this is the one where you might trip up because if you put in that, like in Excel, that's not the right operation, but it's times is exponentiation in Python. For some reason, it's done this to me a couple of times today. It throws an error, but actually it works fine, and there is no error, and I don't know what's going on there. But anyway, so you can see even with kind of taking the time to chat through it, and even with not being the most familiar with Python syntax, there's probably less than 5 minutes to get out all 7 levels of the regular case using Python. So that was not the intended solution. The intended thing was that you'd have to do clever things with formulas to be able to work with it. So now let's go and talk about how to do it, doing clever things with formulas. So there are 3 functions that form the core of my solution to this. The first one is just called diglist, digit list, and you just give it a number, and it gives you the list of the digits in that number. So 588049 da 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 is from here, 588049 da da da. It also has an optional argument to give the digits in reverse order, so 00803 is from the end of the number here, 00803. That becomes relevant later, but we don't need it right now. So for level 1, to sum up the digits, it's just sum of dig list of this. And I'm deliberately being a little bit, magical black box about the lambdas right now because I'm going to be doing a series of videos about lambdas and the benefits of working with lambdas over the next few weeks. I just want to give you a sense of, if you have the right lambdas, how smoothly a complex case can flow. But once I've gone through it, I will also then show you how these lambdas work. But for now, all you need to know is you have a lambda that splits a number into a list of digits, and you're away. So then here, because we know that there's no carrying, we can just do sum of digit list of this plus digit list of that, and it all works fine. So now that's the first operation, is digit list. The second operation we're going to talk about is what I think of as accumulation, and that's going to be the trick to managing the carrying, but also the trick to everything else that comes later. So flip over to my slides and give you a quick introduction to what I mean by this. So I'm going to show you naive addition and accumulating. So naive addition just means we're going to add these up term by term. 1 plus 2 is 3, 2 plus 9 is 11, 3 plus 8 is 11, 4 plus 7 is 11. So the answer is 3, 11, 11, 11. Obviously not. And so you've almost certainly done this in elementary school. My kids are learning it right now. We're going to start from the right, work our way over to the left, and carry digits across. So first, we're going to turn that 11 into a 1 and carry the 10 over into the next column as a 1. So you add that 1 to the 11, it becomes 12. Then you repeat the operation here. Just keep the 2, move the 1 across, that becomes a 12, and then do it again. And you keep doing that until you get to the end. And then the number that you have left here is your correct addition of those terms. So again, I'm not going to show you all the details, but let's just go 3, 11, 11, 11. I have I'm going to put the 3 at the bottom because this is designed to work with them in right to left order. So I have a function here called accumulate. It takes that. Don't worry about the extra 0 it adds because we're looking at digital sums, so it doesn't make any difference, but it rolls these up from right to left exactly like I described here. So if any part is greater than 10, that part gets carried over to the next column and added in, the digit is kept, and then you keep doing that until you get all the way to the left-hand side. And so once you have that, you just need to, first we're going to take the digit list of this and add the digit list of this. And sorry, I want them in reverse order because, like I said, the accumulate function that I wrote starts from the right-hand side. So that's why the digit list had the option to reverse. So that gives me my naive addition. Then I'm going to accumulate on that. And that gives me my answer number. And then I need to take a digit list of that again, and then sum that up. And that works nicely. And now the interesting thing, and I won't claim that I realized this at the time, I built addition and subtraction slightly differently, but if you think about it, we talked about naive addition, so let's look at naive subtraction and accumulating. So 2 less 1 is 1, 9 less 2 is 7, 1 less 3 is -2 or -2, depending on where you live, and 4 less 6 is also -2. So then you do your accumulating, but instead of carrying, you're sometimes pulling from the next one over. So you bring 10 across from here, you add that to the -2 and -2, and you get 8. Now you've got -3 here. And then you repeat that again. You bring 10 over from here, you add that to the -3, and you get 7. And here you've got a 6. And then you've got your answer, 1678. So it's actually the exact same sort of algorithm to apply, which means no new functions, no new logic, no new anything. I just changed that plus to a minus sign, just like we did with Python, and it feels super easy. And then the last few levels are about multiplication. So let's quickly explain the sort of equivalent to naive addition, naive subtraction with multiplication. And the way to think about that is if you've got two 4-digit numbers you're multiplying together, say 6410 and 1473, if you multiply them digit by digit in a table like this, so 6 times 1 is 6, 6 times 4 is 24, 4 times 1, etc. If you take each diagonal of this, that will correspond to the same power of 10. So this is multiplying two numbers from the ones position. This is multiplying a number from the ones and the tens and the ones. So that's going to end up in the tens position. Again, naively speaking, it's going to end up in the tens position because then we'll have to deal with carrying. This is going to end up in the hundreds position, the thousands position, 10,000s, 100,000s, and millions. And so you add up along each of those lines, and you get 0, 3, 19, 50, 59, 28, and 6. And then you just need to accumulate through that in the exact same way as before. So you get 0 stays as 0, 3 becomes 3, 19 becomes 9 and carry 1 across, 51 becomes 1 and carry 5 across, 59 becomes 64. So you keep 4 here and carry 6 across, 28 becomes 34. You leave 4 here and carry 3 across, and the 6 becomes 9, and you're done. So I wrote a function that does that. I'll take you through the logic of them all later, but for now, I'll just show you. We've got a multiply big, multiplies this number by this number, and that's the answer. And it's very big and long, but no problem. So then we need to say multi big of this with this, and then we need to take the digit list of that and sum it. And that's not so bad. And then we come down to level 6. And here with this setup, it's going to be very easy. We're just going to take the result of multiplying the first two numbers together, then multiply it with the last number, and everything else stays the same. Nice and simple. And then, and again, with this setup, like similar to, when you get addition in a smart enough way, levels 2, 3, and 4 all fall out at the same time. If you get multiplication in a neat enough way, levels 5, 6, and 7 all fall out at basically the same time. So here we need to apply the operation repeatedly, and so a great way to do that is with the reduce function. So we're going to start with this value, and then, so we want to raise it, in this case, to the power of 4, meaning multiply a times a times a times a 4 times. So if we're starting with a, then we need to multiply 3 more times to get that. So how many steps are we going to take? Just the exponent minus 1. So this is just going to be 3 terms. And then the lambda that we apply, so it's to what we've accumulated and the current value. And the lambda is going to be big mult big of a, the number, ac, I've called it here, the number we've accumulated so far with the original number. So in other words, all this is saying is start with this number, and then, because we want to get to the 4th power 3 times, multiply that number with itself. And that'll give us some enormous string of text, and then, same as before, we just need to wrap that in dig list to get a list of digits, and wrap that in sum to get the sum of those. So all very neat, and then let's take a quick look at the bonuses. The sum of all the digits of the numbers in every question, excluding the examples. So here I actually set up a placeholder for it. So in this kind of situation, you want to kind of grab all the digits together. One way to do that is we can say filter of this down to the end, back up, where are we? so we only come 3 columns out, so G, H, and I is the most we ever have, where we can just say is number the game number column, because everything except the numbers 1 to 120 is text. So we filter that. That gives us all the numbers, and then we can we want to get rid of the zeros and flatten it out. So we'll do toCol, ignoring blanks, and that flattens it all out there. And then the digit sum, we just again we've got it all set up. This is the nice thing about working with lambdas. Once you have them set up, it's very smooth to use. So the first bonus question is what's the sum of all the digits, and we can just do that, and it's 50,000. Then the next question is what is a plus b, where a is the number of numbers across all questions excluding examples that are divisible by 3, and b is the number of numbers across all questions excluding examples that are divisible by 8. Now this one requires that you know some mathematical tricks. So for division by 8, the thing you need to know is that 1000 is a multiple of 8. Because 10 times 10 times 10 is a multiple of 2 times 2 times 2, which is 8. So in other words, when you're thinking about divisibility by 8, anything times 1000 is divisible by 8. So a number is divisible by 8 if and only if its last 3 digits are divisible by 8. So in this case, we can say mod right of this 3 by 8 equals 0. We'll tell you yes if it's a multiple of 8, or true if it's a multiple of 8, and false otherwise. Then for the multiple of 3, the thing you need to know is that the position of a digit in a number doesn't change what it contributes to the value mod 3. So in other words, for example, if I have a 1 in the tens place, or if I have a 1 in the ones place, the contribution is the same because the difference between those two is going to be 9 times something, or 99999 times something, which is always a multiple of 3. So in other words, shifting a 10 to a 1 or a 100 to a 10,000 or anything like that doesn't change the value mod 3, because you're always adding or subtracting a multiple of 3. And what that means is that a number is a multiple of 3 if and only if the sum of its digits is a multiple of 3. And that is a much smaller number that you can plug into an Excel function. So here we're just going to say mod of that by 3, equals 0. So we're interested in how many multiples of 3 and how many multiples of 8. So then we can say countifs. This is true. All happy? Then add all 40 numbers together in level 3. All numbers in questions 21 to 40, excluding examples. What is the sum of the digits in the answers? So that's here, 21 to 40. The nice thing, I didn't mention it before, but one small piece of generosity in the middle of being a total douchebag that Michael offered is that all the numbers in any given level are the same length. So here we just have 40 numbers that are of length 50. So let's see, do I have the space to do that here? Yes, I do. So first, what you can do is toCol all the numbers, and then we just want to get the split the 50 digits into columns. So we can say mid of that. This is going to slightly give away how the digit list lambda works, but that's fine. So sequence. So we're going to go numbers 1 to 50 across and 1. So in other words, from each of these numbers, I want to take one character from position 1, one character from position 2, 3, 4, 5, 6, 7, 8, all the way up to 50. I multiply that by 1 to turn them into digits. That's going to cause a spill error, so let me just shift it over here for a minute. So that gives you that, and then we're going to start by naively, I want to naively add these up and then apply my accumulator, but that means I need to have them in reverse order. So we're going to actually start from 50 and go in steps of -1. So then, let's see, 368, is that? Yes, first number starts with 368, so my first number ends with 863, which is good. So then I want to sum those by column, which is bicol sum, if you're lucky enough to have the eta lambdas. Otherwise, it's bicol lambda col sum col. And then we're going to accumulate that. And that gives us the total value of smashing all those numbers together. And then we're interested in the sum of the digits of that. So we're going to say dig list of that, and then sum of that. Okay, then subtract the smallest number in level 4 from the largest number in level 5, in both cases excluding examples. What is the sum of the digits of the result? So first we need to get the smallest number in level 4, and again we can't use min on these because they're too big, but what we can do, because again they're all the same length, we can just use lexicographic sorting to put them in number sorting. In other words, if numbers are of the same length, then if you just sort them like words, in other words, first by the first character, then by the second character, and so on across, then they'll sort in the correct order. If they're not the same length, they won't do that. Like 10 will come before 2, for example. But again, here they are, so we don't mind that. So I'm just going to say what I want the smallest from L4. So let L4 small be, so we go to L4. I want to call that, so that'll flatten it all into one list. Then I want to sort it in order. And then I want to just take the first element from that, so I can just use at. You could also use take with 1 or index or whatever, but sort is neat. So then L5 big will be, again, we're going to do at sort to call. So we're going to flatten level 5 inputs out into a column. We're going to sort them, but this time we're going to sort them in negative reverse order. So that gives me L5 big, and then I'm interested in digit list of L5 big, 1 to be in reverse order, minus digit list of L4 small, again 1 to be in reverse order, and then I want to accumulate that. And let's just take a look at that for a second. That's not the answer, but let's just look at that and make sure it's, that is some enormous big number. Great. And then we're interested in the sum of the digits of that. So we'll just call this diff. And we're interested in sum of dig list of diff. Okay. And then this is a fun one. Again, a little bit of mathematical trickery required here. What is the sum of the digits of 4 tetrated to the 3? To the 3. Tetration is repeated exponentiation. So the question is, what is 4 to the power of 4 to the power of 4? And I guess just to kind of clarify, the order of operations is very important here. So if you say 4 to the power of 4, that's 256. That to the power of 4 is some large but manageable number. But if you calculate the top bit first and then take 4 to the power of that, you get a number with 154 or so digits, which is rather trickier. So the fun thing about this is you basically need to take 4 to the power of 256. If you tried to do the multiplication operation 255 times in the spirit of how we exponentiated down here in level 7, that would be extremely calc-intense. You'll note the warning here. It is recommended you save your spreadsheet before attempting this question. But if you're a little bit mathematically sneaky, then you'll know that if you square a number with a power, let's say a to the b squared is equal to a to the power of 2b. And that means that you can double the exponent in one multiplication. So if you think about it, the exponent, you start off with 1, and then the number, you start off with 4. So we want to double this until now we know that 256, because it's a power of 4, is also a power of 2. So if we just keep doubling, then before too long, we will get to 256. Specifically, we'll get there in 8 steps. And some of these you can just do with regular old Excel, up as far as I think this one. And then if you try to go to this one, it doesn't even want to show it. But yeah, you can see it's got a bunch of zeros at the end, which it shouldn't. So then for the rest of the way, we can do multi-big of this with itself. And keep going, and keep going, and keep going. And then finally, we're just interested in the number of digits in that. Or if we want to be even neater, I just laid this out for sort of exposition, but you could also say reduce, starting with 4, 8 steps, lambda a v, and then we could do big multi-big, keep getting that wrong, multi-big of a with a, in other words, square a, that gives me the enormous number, and then I want digit list of that and sum. and then you can get it all done in one cell. 733. And I think that's all the questions. Yes, that's 1250, which is full marks. So just briefly, I'm sure some people will look at this and say, you know, that's nice, but where's you know, where's a non-insane approach? So I'm going to show you the lambdas in a second, but just for reference, the way that I did this on the day was basically the same thing, except spread out more and less elegant. So for example, here's addition. There's the two numbers. I split them out into digits, and then I just have the kind of manual version of accumulate. So I take, you know, here's what I carry over, and here's the digit. So here, for example, 5 plus 4 is 9. So the digit is 9. I carry over nothing. Then 5 plus 6 is 11. So the digit is 1, and I carry over 1. Then here 7 plus 1 is 8, plus the 1 I carried over, so the digit is 9, carry over nothing, and so on up to the top, and then eventually just concatenated them all together, or summed them up actually. And similar for subtraction. Like I said, I didn't immediately spot how similar they were, so I could have made this the literal exact same formula as addition, but instead I made it a check for, you know, if it goes negative, then put in a -1. And then the multiplication was just the very longhand version. So, you know, exactly like in the slide I showed you, I laid out, you know, all the digits of one number here and all the digits of the other number here, multiplied them all together, and then gathered numbers that were related to the same power of 10, and then tried to accumulate those and blah, blah, blah. It worked fine. I got up to level 6. Yeah, I got level 6 done. It's all broken now because I deleted a bunch of stuff after, but anyway. I couldn't get level 7. The reason I couldn't get level 7 is because my multiplication setup was not clean enough. So it basically all of level 5 and level 6, you only had to deal with 50-digit numbers, but in level 7, as you exponentiated, the number of digits kept changing, and my setup was not clean enough to deal with that. But in principle, it's all the same, just spread out in the grid. So let me quickly show you the lambdas, then I'll show you the crazy level 8 that wasn't. So for the lambdas, digit list is a very simple lambda. The only twist is that I've added this optional argument for reverse. So just add a 1 if you want to reverse. So you know the text number, you take the mid of that text sequence of len of text num. In other words, every number from 1 up to text num. All of this you would just drop if you only wanted to get the digits in one order, but if you want to also be able to reverse them, then you say if you're reversing, start from the biggest number, which is the length of the text, otherwise start from 1, and if you're reversing, then take steps down, -1, otherwise take steps up 1. Nice and simple, really. So accumulate is a little bit more complicated. You need to apply an operation over and over and over again, so you can probably guess that that's going to involve reduce. So the idea is that we maintain a list of two things at each stage. One is what we're carrying over, and the second is the text number so far. So we start off with 0 carryover and a blank string for the text. Then we iterate through the digit list, and again we have to make sure that that's you know, going from right to left in size order, and that's the way we set it up every time we used it. So then what is the operation? So A, remember, is the two-part thing, which is what we carried over and the text number so far, and V is the next value from the digit list, which again, remember that the digit list can be a product of a naive operation, so that digit could be 35 or whatever. So then there's not much more to it, really. So what we need to split is what's carried over. So at A just gives the first piece of A, which is the number that we carried over. We add that to V. So again, if I come back to here, so here in this case, the 12 is the number to split, which is the 11 plus the 1 that we carried over from here. So that gives 12. And then we're going to split that by saying the last digit of that stays here as a digit. In other words, gets appended to the text number, and any other digits of that become the carryover. So that's what we need to split. The new digit is mod of to split by 10. And then the output is we stack together what we carry over, which is the number to split, minus the new digit, which is just the last digit of that, divided by 10. So in other words, all the other digits from there. And then here we add the new digit to to the left-hand side of the text number that we're accumulating here. And you just repeat that over and over again as many times as you have digits. And then right at the end, you concat. In other words, if you still have a carryover after you get to the end, so let's say there was no 3 here, so it was just adding the 3-digit numbers, and there was no last column. Then when you got to this stage, you would still need to carry a 1 over into a space that you didn't have before. So at the end of the operation, you get the final carry and the text number not including the carry, and then you just smash those together. And that's why the extra 0 there is why you saw some kind of funky zeros sticking around in the other places. But that's the idea of accumulate. And then multiply, again, is just very similar to the sort of all laid out spreadsheet I showed you. So it's a function of two numbers, a and b. The numbers from the first one is digit list of a, and 1 to be in reverse order. Numbers from the second one is digit list of b, 1 to be in reverse order, and this one is 2 row. So we've got 1 going down the column, 1 going across the row. Then the products, which is basically these numbers, the naive thing but summed across the diagonals, is we're going to group by. So the numbers we're going to group are nums1, which remember is going down the column, times nums2. So that gives you a grid of numbers, and then we use toCol here to flatten that out. And then what we're going to group it by is this here, which is basically saying number down the rows, so like 1, 2, 3, 4, number across the columns, 1, 2, 3, 4, and add those two numbers together. So in other words, here would be 2, both of these would be 3, all three of these would be 4, these would all be 5, these would all be 6, these would all be 7, these would all be 8. And then we're going to, again, flatten that with toCol, and then we can group by those. So in other words, anything that's on the same diagonal, that has the same sum of the sequence this way and the sequence this way, gets added together. So we group by with sum, and then 0 and 0 for no headers and no totals. So we just get a list of all the kind of diagonal sum numbers and the totals along each of those. So then we just drop the labels on that, which is the sum of the sequence numbers. So drop the first column of that, and you just get this exact value here. Then we apply accumulate to that, and that is the answer to the multiplication. And then this is where I added a trim check, because as you saw, my accumulate kind of added zeros onto the beginning, and that didn't actually cause any problems with the main question, but did cause some problems with the level 8 that I'm going to show you in a second, so I had to clean that up. And the way I did that is if you just multiply the number by 1, Excel will trim off, like turn a bunch of digits at the end into zeros, but it will still be the right length. So then you can take the length of that, and then you can take the right of answer to that many digits. So in other words, if there's 15 zeros at the start and then 45 other digits, if you multiply it by 1, you'll be left with a 45-digit number. And so you want to take the right 45 digits from your starting number. The only twist is I initially just said length of answer, and if you don't format it as text like this, then it says, well, answer is whatever, 1.675 E37, in other words, by 10 to the power of 37. And so the length of that doesn't grow with the size of the number. So you have to specifically tell it, format it as a number, not scientific notation, then take the length of it, then take the right. So that's all just a kind of an extra caution. All right, we're over half an hour, so I'm going to wrap it up pretty quickly. So that's the lambdas. That's how I use them. That's the Python. Let's quickly talk about level 8 just for fun. Michael told me that he had offered this level, but that he had no idea how to solve it, which is fair enough, because sometimes to write a level is easier than to solve it, right? I've actually just taken, he didn't make this level 8, I guess he had his own version, but I've just taken the pairs of numbers from one of the other levels that had pairs of numbers, multiplied them together to get some enormous number, and then given the product and then one of the other numbers as the input. And the challenge is to divide and get back to the other number. And it was probably a good decision not to include this question, because even with this required, sort of built on a smoothly running multiplication and subtraction, and even then it was quite a lot of work. So here's what's going on. I'm just pulling out one level so that I can data table it. So here's the starting number and the starting divisor. Then do a little bit of setup over here, which is we multiply that divisor by every digit from 1 to 9, check the lengths of those, and then take a long version of each of those, meaning as many digits as the longest one. So in other words, if we multiply it by 9, it starts off as a 50-digit number. If we multiply it by 9, it becomes a 51-digit number. So then for these first couple of multiples that are still 50-digit numbers, I just add a 0 to the start of them, so that they're all, again, the same length. Because if they're the same length, then we can use sorting to figure out where something belongs. So then the idea is that, so here we've got 51 characters in all these multiples up to 10. So we're going to take the first 51 characters of the number, sort it into this list, and figure out where it ends up. And based on that, we'll be able to figure out what's the biggest multiple that we can take out. And then this is just the filter of that for the ones. So if you're multiplying by 1 up to 9, then the number of digits can only change by 1. So here we're just filtering for where the number of digits is less than the max, because you might need to. And so that way, if you have less than 51 digits, then you just use this, sort it with these 50 instead. So what does that look like? Well, we say here's the enormous number. Where am I? Yes, so the biggest multiple of the divisor here, the 50-digit number starting with 455, the biggest multiple of that you can take out of the first 51 digits here is 3 times that, which is this 51-digit number starting with 136. So you subtract that off, and then you're left with this number, which is, you can't see it exactly because this is too big, but you can see now that it's like 1 digit shorter, and you can match that into this table here to figure out, okay, so that we subtracted off 3. And then you can compare the lengths to figure out, okay, so it's 3 by 10 to the power of 49, because this number is 49 digits longer than this one. And then we just repeat. So it's exactly like the sort of division algorithm that you probably learned in school. You take off the biggest multiple of 1 digit that you can first, subtract that off, and then carry on down. And I just did a bunch more spaces than I actually used just to be on the safe side. So eventually, Michael did say he didn't expect people to do non-integer division, so it did end up being a perfect multiple. So at some point, you subtract off the number itself, you get to 0, and then we do a sum ifs. So sum this number where this power of 10 it's being multiplied by is everything from 1 up to 50, and then we accumulate that. So in other words, start with the so you got a 6 and a 1 that are in the ones position, then you got a 7 in the tens position, a 4 in the hundreds position, and so on across. So you add those up, accumulate them, and then again this kind of length check here just to make sure that we don't have any extraneous zeros. And then we do a data table to run that for all 20, and that's it. It's definitely possible to take all that's going on here and smash it into one recursive lambda, which there's probably only one person who's going to hear that and say, I am interested in this challenge, but Bo, if you're watching, I look forward to seeing what you do with this. Oh, battery running low. All right, well, better wrap it up. I think that's the end anyway. Let's see. Yep, that's everything. My long promised series of Lambda videos is starting next week. So if you looked at this and said, oh yeah, it's great to be able to solve the whole question in 10 seconds using lambdas, but how the heck do I write something like this? I got you. It's coming. That's all I got for today. Thanks for watching. See you next time.